Good morning, good evening. How you all doing? So we just got done with Portland Vice. It was a great time. Uh, Met a lot of cool people. Saw a lot of good talks, and wish you guys could all have been there. So I gave a presentation creating a slicer profile using resonance testing. The reason this came by, before that, I'd like to thank Draft Shift Design for letting me test this out. These are the StealthChanger folks, really great guys. They helped me create this presentation, kind of sounding board. Uh, this presentation, creating a slicer profile using resonance testing, was my presentation. I stated that I would make this video and upload the presentation to my GitHub, so I will do that. This is why I'm doing this. A lot of good questions, a lot of interesting new information that I'm now incorporating based on the questions that were asked. It's going to be incorporated into this, so you guys are getting a better presentation, I guess, than the Portland Vice, or an updated one. So, who am I? I'm Reth. Uh, that's who I am. This is it's my secret agent. These are my degrees. I work at the patent office as a semiconductor examiner. I am not a mechanical engineer, as many of you know, so a lot of this was just learning as I go and reading different things and talking to different people. This is my cover CYA notice here. Yep, there we go. All right, background. What is resonance? So resonance, basically, every system, everything has a resonance. It's just the natural frequency at which it will oscillate. Uh, the Vorons oscillate, all 3D printers oscillate, and the goal of Input Shaper and all this testing is to minimize or cancel out the resonance happening, and this shows up as ghosting, or it's also called ringing or resonance on your prints. It's that wavy pattern that happens. Damping ratio is the loss of energy based on the resonance. So it's how much energy it's going to lose. Ours are, I believe, they are critically underdamped, critically overdamped, based on the value. So this is a standard damping ratio value, and the charts you can think of this as the width of the peak. Standard Clipper sets a standard value of zero point 0.1, which is kind of high for a lot of Vorons and many other Core XY printers, but it's a good all-around value. We're going to exclusively use Shaketune in this. Shaketune has some features that standard Clipper doesn't offer. There's also another one called Res Helper. Res Helper is, you can think of it as standard Clipper with extra. It calculates a damping ratio, but it does not incorporate the damping ratio into the input shaper graphs. And that, yeah, so let's just do this. We'll do it real quick. Your damping ratio here, all of these values that you see here, you'll see ZV, MZV, right? These are all your shapers. All of the other values out here are calculated from your vibrations, your smoothing values, and your accelerations. They're all calculated values. All of these values use use damping ratio. So if your damping ratio is not your actual damping ratio, so if it's a Clipper default, these numbers, especially your accels, all look higher, and your vibrations all look better. And then your smoothing is, I believe, it's lower. Once you put in a real damping ratio of your graph, uh, your everything will drop. Your vibrations will go up, your smoothing will go up, which means you're doing more smoothing, and your accels will drop. So these aren't real numbers here. They're good enough. They're good enough, but they're not real numbers because they're based on this default value. Why do we worry about resonance? This is the ghosting I was talking about right here. You can see it right here. This is the ghosting and ringing. It happens like this. You got to be careful though, because VFAs sometimes will look like ghosting or resonance, right? So this right here is more, if it's consistent across, it's going to be more VFA, which is motor based, than ghosting, which is acceleration based. But we're going really high in accelerations from where we started, right? So Mark III, these were our accels, Vorons. This is the standard Vorons you'll see in most slicers. It's low. It's on the low end. This is the low end of what a standard Voron could do. But we have no slicer settings, or all the information from Ellis print guide to the built-in slicer profiles for Orca, Prusa Boss Edition. They're all set at these. We can do better than that out of the box. And then what happens when you do all-wheel drive, or four motors, or quad motor, as some people like to say? How do you determine that? So that's the point of this presentation, or this talk, is to actually figure out using Input Shaper, using mainly Shaketune by FrixX, how we can get faster speeds, faster accels, mainly faster accels, at the same quality or better than we were doing before at these values. So that's why the as you can see, I wrote a bunch of issues down and I just talked about them, but it's really coming down to we're pushing these machines faster. We are learning more about the kinematics and the motion system and what it takes, toolhead design. We're blowing past the standard 3000, Excel is in all the profiles. So what do? What needs to change? How do you change it? Where's a good starting point? That's what we're going to be talking about. So this is my test print. It's called Bog. It's a V2 350. It's Bog because it's black, orange, and green. It's using the Vitali's 9mm all-wheel drive. I have LDO Kraken motors. I'm using a Dragon Burner and a Sherpa Mini. In your accels, a lot of your accels are going to be limited by your toolhead design. You want a toolhead with a good center of mass / center of gravity, which the combined weight of your toolhead should be somewhere in the middle of your X linear rail carriage. Stealth Burner, which comes standard with most Vorons, is a really bad center of mass design. It's a good print head. You can't push it to speeds. As you get smaller and more designed for the center of mass, center of gravity, you'll find that you can actually push higher accels. I'm using a Carto, and then EBB 30. The 80 accel I use, as if you guys watch my other videos, I just recommend you use the toolhead board, whether it's EBB 36, Nighthawk 36, Nighthawk SB. For my purposes and what I'm going to talk about, that's the best one to use. So these are my current print settings. We're going to go through and we're going to start figuring out all these things, right? We're not doing line width and all that stuff. We'll mention it. It does have an effect on how fast you can print, mainly your speeds. But we're going to go through and we're going to try to recreate this using the charts. And now there's stuff that's going to happen, and like I'll say, our basic starting one will be, say 15,000 Excel. But in the end, we'll drop down to say 5,000 or 10,000, and I'll explain why. And it really all comes down to, at the end of the day, we're looking for good prints. Right? So this talk is based on printing good, having good quality looking prints, and not necessarily printing fast. Because if you want to print fast, just throw everything at 11 and just send it. But personally, I like to have good looking prints, and I want to have them looking good as fast as I can go. So we're going to use Shaketune. This is by FrixX. It is currently the best one you can use to determine your input shaping and your resonant or your motor vibrations. No other programs really do motor. There's nothing else out there really doing motor vibrations to cancel out VFAs, find good speeds. A lot of it is, in the past, if you had a VFA, which is a straight vertical lines, people would say just print faster. And then that's true, but you could be printing faster into a bad zone or bad speed zone. This is the belts from Shaketune. Standard Clipper, Standard Calico have this built in also. This is just for completeness. We're actually not using it. So these are my input shaping graphs. They are not single peaks. This is an all-wheel drive system. And the reason they're not single peaks is toolhead. So this is tool head. This is tool head, right? These, I'm getting these, but even though they're not single peaks, let's see if I can blow this up. You can see here that EI vibration is still 0 right there. So what does that mean? That means the shaper is doing its job. And you can see here, even though I got 2 peaks, the shaper's canceling out, giving me 0 on my vibrations. The Y, similar story, but the Y has a little residual. So the Y's got a 0.1. It's not going to be a big deal. We're not actually going to be pushing, in the end, we're not going to be pushing at 13,900. We're going to go slower. And the reason we're going slower, we will be going slower, is I print PLA mainly, not ABS or any of the other higher temperature ones. So I have cooling issues. So my greatest limiting factor is cooling. And I know there are other solutions, other tool heads that will allow me to print PLA faster. The problem is the fans become loud. You need to start pushing more air at it. You either have to go with server style fans, which are incredibly loud, or you gotta go CPAP, which can be incredibly loud for PLA. So I'm using the standard Dragon Burner fans or Zoll fans or something like that. They're relatively quiet, and it wouldn't be such a big deal if my printers, I have about 7 printers constantly printing, 10 printers total, if they weren't literally next door to me. So I'm working my office. They're right next to my office, so I can't be printing faster than basically what you'll see because of cooling issues. So it's likely tool head, as I said, lack of frame support. So as you go all-wheel drive, the rigidity of the frame starts to play an effect on your input shapers and how fast you can go. So Monolith has one where they use the actual panels as frame support, drill holes in the panels, screw the panels to your printer frame. That's how they stiffen the frame. Traxman from StealthChanger, he has braces, side braces that you can use. He's designed to help stiffen the frame. So at all-wheel drive, frame stiffness starts playing into effect. This is the one test that's unique. It's called the vibrations profile. This is unique to Shaketune. This test will attempts to give you the vibrations caused by your motors. So this is going to be your VFAs. This is the test you're going to use to determine the best speeds for VFAs. It's ran at a relatively low acceleration. And the reason it's run low is because what it's trying to do is just speed those motors up, get them from 0 to, for example, 75 millimeters as fast as possible without having too much ringing or ghosting going on, right? It doesn't want that tool head to start moving around. So it's a relatively low acceleration, but its goal is not to give you an input shaper test. Its goal is to give you what the motors are doing. More testing. I need to do more testing on this, to be honest with you, to test this, say, at my actual print speeds and see if it changes dramatically. I haven't done that testing yet, but I need to probably do that. So right now we're going to set the slicer. Yay! So we're going to start with accelerations. So we've run input shaper, we've run the vibrations test, we've nailed down all the stuff. We got it as good as we can get it, or good enough, or good as we like it. So let's start putting it into the slicer. So a couple notes before we start that. Clipper does not have a jerk value. I believe that's a Marlin value. And jerk is just the derivative of your acceleration. So what Clipper uses instead is what's called square corner velocity. It is how fast are you going to take a turn, a 90-degree turn. A good starting point for SCV is 1,000. Your Excel divided by 1,000. And we'll go back up one. So this one is run at 5. Okay? If you want to optimize the square corner velocity, you're going to run this test, input shaper, at the standard 5. You're going to get a value, 13,930. Right? You're going to divide that by 1,000, so you get 13.9. Shaketune allows you to input square corner velocity as a variable to the test. So it will run the test and do the calculations with your square corner velocity of whatever you set it. So you run this test again and you set square corner velocity to 13.9. You then look to see, after it's done, you come back over here, you see what this Excel is. And what you will find is as you increase square corner velocity, your accelerations will decrease. So it can't do both. It can't get you super high square corner velocity and super high accel. If you set square corner velocity, say some number like 100, don't be surprised to find that the shapers are going to set your max accel at 0. Like they can't compensate for that. That's just not going to happen. There is a point. There's a sweet zone, right? So we set it for 13.9. It comes back. It says this drops it down to 12. We are then going to run the test again, setting square corner velocity at 12. And we're looking for the point where the value we put into square corner velocity matches or close enough to the recommended max accel. So let's say we put 12 in and we get back 12.7. Okay, we take 12 points, take the 12.7, we'll put it back in, and then let's say now we get 12.3. We're good enough, right? We're going to stop there. But if we see something like 11, we're going to keep dropping it down. And this is way we can. It's an iterative process. It takes a bit of time, but you're going to optimize that square corner velocity for your system. So it's a good starting point to figure out that value, because that value comes into play for all of your accelerations. And once you find a good value, we'll then use that and keep going with the slicer settings. Right, so that's the example we did. So we're going to start here. So we're going to use EI at the lowest at 0.1. You really don't want to use 2 hump. Smoothing goes up a bit. All-wheel drive, smoothing is not such an issue. In 2-wheel drive, your smoothing would go from, say, 0.4 to like 0.1, which means it couldn't resolve as many fine details. It's going to smooth over the fine prints or the fine features in your model. Now, maybe you print printer parts, right? It's all structural stuff. You don't really care about smoothing. That's fine. You just want 0 vibrations. There's different reasons to choose ones, but you kind of want to stay away from the 2 hump and 3 hump. EI is an industry standard. It's just out there, right? Everyone's got EI, ZV. All of these are basically known shapers in the mechanical engineering world for cranes or whatever. These are the ones they use. MZV was made as a compromise between ZV and ZVD. ZVD would be the middle one. It's more of the we'll call it industry standard or well-known shaper. It lies between ZV and EI. The guys at Clipper did not like the result of ZVD, so they made MZV a shaper. As you can see, that's got 0.7 in Shaketune. So EI, I like EI. It's a known quantity. It performs well. I lose some accel, right? So here I'm losing 500 accel. Not a big deal. It generally will get you 0 to very, very low vibrations. So we're going to set the X. This is going to be, we're going to use this value right here as our exterior or external perimeter value. And the reason is because that's where the ghosting happens, right? So that's going to be our base. Everything's going to be based on exterior perimeters, exterior features, because those are the pretty things. Those are the things we want to look nice. And as we go in from that, we can get things to look a little ugly because no one's going to see them. So we're going to do, this is wrong. This is actually for something else, but we'll talk about that. We'll just go that. Just a ching, ching. There we go. So A safe starting point, you're going to set this as external, right? Boom. A safe starting point is 500 more than that. Now this whole thing we're going to be talking about is just starting points, right? Based on the graphs. You have to do tests. You have to do prints to figure out what is the actual one you're going to do. So we just do the math like we just said. Here we go. 13.9, 14.4. A default, set it, just leave that at whatever the standard slicer profile says. Just leave it at the default because we're going to move everything. Everything's going to get filled in here. Minimum cruise ratio, leave that at the default 5. That used to be called, had a different name. Just leave it at 5. We're not going to talk about that today. And then jerk, as I said, is square corner velocity. Leave that at 5. So that's kind of our default for everything. If it's 0, it uses the default. So now we have the perimeters and external perimeters, and these perimeter values should say internal perimeter values. But that's where we're at. So the next thing we're going to do is we're going to set the sparse infill. So this is this stuff. There's a couple things we need to do before this. We need to set max volumetric flow rate. And what is the max volumetric flow rate, right? It's how fast your extruder and your hot end combination can push filament out. It's generally limited by your hot end until you get something crazy like a tube or some of the other crazy ones where it will be limited by your extruder. The easiest way to set square corner velocity at this stage is just Google it. Just what is my max volumetric flow or my max flow rate for a Revo, right? Or a Rapido or Rapido Ace, whatever you're using. And we're going to put that in the slicer. And I'll show you that in a bit. Just put it in there, and that's going to be the limiting factor on our sparse infill. That's going to kind of be like our safety net so we don't get too crazy. But if we want to get crazy, we can just not use that value. So what are we using? This is all going to be based upon the max accel. So Ellis has a test called max accel or max speed acceleration. You're going to run that test to figure out the combination of your max velocity and max acceleration. So there's a correlation between the two. You can't just go, if you run it at max speed and say it comes up with like 1,000 millimeters per second is your max speed, and then you run acceleration and it says 60,000 acceleration is your max accel. You can't just put those two together because your system's going to skip. You need to run the test. The max, I think he makes you set max accel first or max speed. You pick one, you start with that. You then use that one and figure out the other one. So if you start with max speed, you say you got max speed of 1,000, right? Then you run the test and you use that 1,000 in the max speed test or max accel test, and it may come back it's like 5,000 or something. It's a trade-off. So you can't get both. You've got to pick which one you want more, and then use that to determine the other one. For 3D printing, if you have to choose, you choose acceleration over speed. Because you want to be able to go from 0 to print speed as fast as possible. Because if you have a low acceleration, it's going to take you longer and longer to reach your max speed. And we're not driving cars here going down the freeway, right? We have limited space. 300 beds, you got 300 millimeters. So if you go from one side of the bed to the other side of the bed, you want to be able to do that at speed and as quickly as possible. The quickest way to do it is to raise your accels. So that's why it's always acceleration's better, right? I have a bed plate. I have it using two-wheel drive. Let's say it's 5,000 accel is my half fastest. If I just go to all-wheel drive, I can go to 10,000 accel, and it basically cuts down my print time for that same model by half because I can get to the speed faster, if that makes sense. So what are we looking for in this? We want to go push our infill. So the end game, right? We're going to talk about the end game here now. You're going to set this. I gave some defaults, right? 8 to 10,000 for two-wheel drive, 15 to 20,000 for four-wheel drive. Those are kind of like defaults you can start with. You are looking for, this is perfect infill here, right? You don't need it to be perfect. You don't need that. You can go faster than that because we're going to be putting layers on top of this. But that's good infill. This right here is bad infill. What's happening is it's so broken, you're getting little boogers, little things sticking above the plane. So if we consider this, the nozzle is going to come across this here. You don't want the nozzle to hit anything. This is too fast. This is too much acceleration, too much velocity on your infill. You can solve this by slowing down your accels or slowing down your speeds, but this is not what we're looking for. This is almost what we're looking for, except it's got hanging. Let me blow this one up. Your infill does not need to look pretty. So you see this right here? This makes it bad. Because the next one that comes across is going to go this way. It may start pushing the infill above. So what you want is a thread or a line to come from here all the way down, but it can get thinner. It can start getting like little wispy. So you see this right here? The stuff going up. Eventually it could start curling, and then your nozzle's going to hit it, and then you're going to skip a step. It's going to build up and start turning into this. So this is just a little too high. You want this piece, take this piece right here, you want this one to go fully connect, but it can start to thin out. You know, like you're dropping like you do like Elmer's glue down, right? It starts really big at top, goes kind of thin at the bottom. That's what you're looking for. So this was just a little bit slower, right? This is too much here, right? Because it's broken in multiple places. So you're looking for it to be all the way over. Doesn't have to look this pretty, but it can't. This is just a little too much. So that's what we're doing, and that's a print though. That's after we've set this. So these are going to be our defaults here. So what do we start with? I went with 20,000 at 20 SCV. That's for me. That was what the good range was. Remember, this is an all-wheel drive, and I can push it that fast. And because I use my hot end combination with my extruder, I'm using a 0.5 nozzle for this purposes. So I use a 0.5 nozzle at 0.4 line width settings. I can get this little extra out of it. And this is where I get that little extra. So after that, you go to top set solid and top infills. They need to be less than the sparse infill, because what they're doing, if we go back, we'll pull up the slicer now. Why not? Let's go to this guy. So these are some Matt Meyer makes capybaras. This is on the Rapido Ace, is the hot end I'm using on my bog, the one I showed you. So let's see. I'm looking for something closer. I'm looking for something here. I'm waiting for it to start sealing up here. Lots of perimeters. Is it going to seal? I might be better off with the Voron cube. We'll just do this. We'll go here. Boop. Okay. Went away. I'm not doing so hot with controlling this thing. Okay. Alright, so there's our infill, right? Then we have it's almost like a bridging layer. It's called bridging infill, and it's just going to cover that first top. If we had boogers and crap on this layer, it's going to get translated on this layer, and that becomes a problem because now I have a hump and I'm putting a whole bunch of material on top of it. I'm getting a bigger hump. It's going to be a little smoother, but it's going to be a bigger hump. And if it's broken, completely broken, like the infill, it's going to dip. It'll be a problem. So you want the infill to be almost solid, so that the next layer, this bridging infill, goes on top of it. The next layer is your solid infill. You want this because we're going to be building the top solid infill, which is the very top layer on top of this foundation. This is going to need to be a little prettier, right? So we go ugly. Got it. This is basically the same stuff as your solid infill. Ugly, a little prettier, really pretty, because that's what people are seeing. So for this, you need to slow it down a bit, because what can happen as it comes this way, right? So you see it's all loops here, and it's based on the setting I have. Uh, it's going to turn. You don't want you don't want to go so fast that it puts a pile of stuff here or doesn't put enough material such that your infill doesn't connect with your perimeter, right? So you could, if you go too fast, you may end up with little gaps here. So you want it to go fast enough that it's, can complete this layer in a timely manner, but not so fast that you're either putting too much material here or not enough. So you make it go a little slower. The little slower we're going is we're going to start. The good starting points are the standard Voron values in the slicer for two-wheel drive, for four-wheel drive, or the Ouroboros even from Ishuk would be take your previous external perimeter, this guy right here, and 5,000. You can use that, so we can use 13,900 as our solid infill, which is right here, or we just take 5,000 less than infill, right? So our infill's at 20,000, or we drop it down to 15. We get 15 square corner velocity. The top solid infill, because it's pretty, I could probably drive it faster. I'm going to be honest with you. I probably could. But you can get artifacts on the top layer, which would, if we go back to the slicer, that's the top layer. Now, on a Voron cube, it might not matter, right? But on, say, something like these guys, let's go back here, right? All of the purple, do we have any top solid infill? So that's all this red stuff here is top solid infill. It matters on this guy because I want this to look pretty, right? I want it to look good. So if I got little holes popping out on all this here, you'll see those holes. I don't want those holes on my top layers, even though it's surrounded by perimeters. So you go slower, right? So this guy, there's my solid infill on this one. Let's zoom in there so we can see it. Right? So I got perimeters, solid infill there, or top solid infill here, solid infill here. If I go too fast and this looks ugly, that means that this layer is going to look ugly, which means this layer is going to look ugly. Right? So that's all top solid infill. So I need to go slow. And if you look at on actual models, you start going down, you'll see that it's the top solid infill is not always a nice shape. Let's go back to this one. A nice shape as this one is, right? That's pretty nice, pretty even, right? But this is a test thing. It's not an actual print. And an actual print, you will get something more like this, right? Just kind of, I just wanted to put some there because it's got a layer above it, right? So it doesn't look as pretty, and you got to make sure that you print it at a speed that it will survive all the models. Because one thing I don't want to do is create an individual slicer setting for all my models. I want to create a slicer setting that will do 90% of my models that I print without changing a single thing. Now you can, if that's not what you want to do, then yes, you can do this for every model can have its own print setting, but I think it's a little ridiculous to do that. So back to the presentation. So that's how we set the solid and top infill, right? Kind of a formulaic, but it's all based off the external perimeters, or we can use a storing Voron value as I did here with the top solid infill. I put it up a bit. So next one is other settings, travel. So travel will be your Ellis print guide, test speed macro, and the fastest you can do combination of speed and velocity. Me, because I'm always a safety guy, I don't want to go too fast, because if you're on the edge of that, right? Let's say you said to that, because that's what I said to do, and you're on the edge. There are times when if you have just something slightly wrong with your model and a nozzle hits it, you'll skip a step, especially at the accelerations we're doing. So just you don't need to go full bore. You will save some time, but at some point you put this up so high, the time you're saving doesn't matter, right? So it's a time versus performance. So you just, I put it at 30,000. I found that was a good kind of, it's fast enough, or it has enough acceleration, and I can get to lower the print time because the travel is where it's going between things. So we set that at 30. Bridging. Bridging is going across. So if we go back to the models here, we go down, put it into view. Keep going down. That's bridging. Going across from something in open air with nothing underneath it. You want to make sure that comes out right. You don't want broken bridges because what happens? One, it looks. Where's it at? Let's see here. It looks ugly from underneath with a bunch of broken bridges and filament hanging down. You don't want that. It's not pretty. And remember, we're doing this for pretty, not speed. So the other thing is above it, you've all of a sudden got infill being put above it, and you want this layer to be nice, so the next layer is nice, and on and on. So I set it at my standard Voron setting, and then with a little bit more, so 2,000. You don't have a lot of bridging. Let's look at those models. Where to go? Let's go back to this guy. So our bridging infill, 6 minutes of bridging. Right? For 6 minutes, look at my perimeters are 2 hours and 41 minutes. My external perimeters are an hour and 53 minutes. So combined, my perimeters take up 4 hours, 4.5 hours. Do I really care about 6 minutes to make the bridging go faster? And this is on a whole plate of, what is that, 12 models. I don't care if I need to go faster. The internal solid infill is 52 minutes. Internal infill is 34 minutes. So if I can make my infill go faster, yes, it will save me time. This whole thing took 9 hours and 30 minutes. So you're once again, the prettiness is the external perimeter, which is an hour and 53. Internal perimeters take longer, so those are going to be your biggest cost savings, along with travel. Travel's not a time that gives you here, but it's going from between models and between features on models. Where are we at? We're right here. So wipe tower. If you're doing like a box turtle or a StealthChanger, and you have anything with multicolor or an ERCF, don't mess with the wipe. Just leave the wipe tower alone. Optimizing the time for a wipe tower is a pain. And the reason it's a pain is to really test it, you have to print something with the wipe tower. Which means you're wasting not just one filament, you're wasting at least 2 filaments. And messing with the wipe tower can have problems with the speeds if you don't actually do all the tests and take your time to do it. Is that your wipe tower can fail. Yes, it takes time to do it. And you could probably get some decrease in total print time, but if your wipe tower fails, it's game over for however many prints you have. You can try to save it. Chances are it's not going to happen. So just leave the wipe tower. Let the wipe tower go slow, and if you want to spend the time optimizing it, it's all going to be practical testing on it to see what it can do. So that's not something we can get from our Shaketune graphs. Other settings, the first layer. So people, the maxim is you print the first layer at a slower speed to get a good foundation for everything, right? But you look at some of these speeds people are and excels that people print the first layer at. It's kind of slow, right? So if I've got, let's go back to the models. If we drop it down to the first layers, right? These are my first layers. It's going to take some time to print all of that. Can I go a little faster at least? Yeah, you can. You can go, I would say start with half your perimeter and then go down from there. If you're going too fast, and you could run it with, maybe put four single first layer testing, four of these testing little squares down, and then go between them and see how well it does. My first layer is being printed at 5,000. I did slow it down from half. SCV of 5. It can do it. So that's why I did it. Short distance travel. This was a question at the Portland Vice. So let's pull up. Let's see what it says first before I give an explanation. All right, what's it say here? Accelerate in short distance is determined by retract before travel. By the retract before travel setting. Okay, so what is retract before travel? And it doesn't want to do it here. Retract before. I have no idea what retract before travel is. Is it this? Retract before. Oh, well, let's do this. Retract. We have retraction, minimum travel. There we go. So that is determined on this value here. Okay, so your short travels in there are the minimum travel after retraction. So how much? Okay, so let's see if I can explain it here. The minimum travel after retraction. I retract. If I'm going to do a retraction, right? So let's say let's do something here. Here we go. Okay. So I just did this, right? I just printed this leg here. And I go a little bit more. If I have, let's go back to here. I have a retraction speed. I have a minimum. It's going to retract if I do a Z hop, right? I also have a Z hop, right? So when I do a Z hop, it's going to retract. But to do the retraction though, it needs to move at least this minimum travel after retraction. So it needs to move at least a millimeter before it does a retraction. If I do like a Z lift, right, and then I retract after each retract on layer change, right, or I retract before I actually move. So going back to here, if this space between here and here is greater than 1 millimeter, it will cause a retraction. How fast does that travel between here and here while it's retracting? That is this setting here, short distance travel. So that's traveling for about a millimeter, right? Right. That is yes, before the retraction. So it's the 1 millimeter before the retraction. How fast is it traveling? It's traveling at default 0. So 0 is short is a default. So okay, so it's just going to be the default, which is 5,000. If you go faster, so this is going to be a stringing issue. This one will determine is stringing, whether you string. Okay, yeah. Let's just go there. If I go too fast while I'm retracting, I could be causing stringing. So I'll get a little fine wisp of hair coming from here to here. Maybe it matters, maybe it doesn't. So if I go slower while I'm retracting, let's say I put it at 0's default, and I say set 0, I set it to 1, or something really low. It will basically go really slowly while it's retracting that up, and potentially suck up all of the filament before it leaves a hair along the line. If I go too fast, it might not have enough time to suck enough up, so that it will leave a hair. You want to play around with that. If you start seeing little wisp of hairs between different travel points or retraction points, you're going to want to play with that value, right? Otherwise, if you're not seeing that, if you're not seeing little wisp of hairs all over the place, fine wisp, just leave this at 0. So that's kind of I print it and I see it, and then fix it. So I say leave it at your 4 on default or your default acceleration. Just that one's taken care of. So there's another one I didn't mention. First object or raft interface. You shouldn't be printing rafts. It shouldn't be a thing. So leave it at 0. And that's how we get this basic settings. So all of these values I've said here, these are our starting points. I should really move these around, but these are all of our starting points. After doing testing later on, this is where I got to. These are the values, and I've been showing them as we're going all around. Settings. All right, so these are the values I'm actually printing this model at. This is at max volumetric speed. I set it to 24, right? Because of Rapido Ace, and we can. The infill is always going to be print the fastest. So if we go to volumetric flow rate here, okay, so it's orange. So I'm only printing that at around 14 in my volumetric, and I got 24 to deal with. Why I'm only printing it at 14? Cooling. I am cooling limited because I don't want to hear loud fans in my office. So I make sacrifices. This is a sacrifice I'm making, is I can't push this faster. Now, all of this so far has all been directed to PLA. ABS, if you guys print ABS or any of the higher temperatures, you're going to have much faster accels. Much faster speeds. Your print times are going to be slower because you can push this to 24. I could push this all the way to 24 with ABS. But I don't do that because printing ABS, which I can print ABS, but I choose not to. One, I have more PLA material to print. Two, when you print ABS, you print at a heated chamber, which means I need to spend more electricity, keeping my build plate hotter. Not so bad for one printer, right? One printer, not a big deal. You throw 10 printers into the mix, electricity starts to add up. At least for that time that you're heating the bed and heating the chamber, 30 minutes, 45 minutes, it adds up. The other thing is the fumes, ABS. I do run Nevermores in all my ABS printers. The standard one, I don't have the Nevermore Max. I don't use that. I have just the regular Nevermores. 50-hour print time, and then you got to replace the carbon. Right. This is 9 hours and 30 minutes. 50 hours, so effectively 10 hours. 50 hours would get me 5 plates, and then I've got to replace it because I don't want all those fumes in my office. That cost adds up. So it is cheaper for me to print PLA, and the amount of things I print, I'm going to go with it. I do sacrifice time, right? So it's always a time versus money, and I'm choosing time to be the winning factor here, so I can get good prints without spending a lot of money. In this, I'm just going to do a little aside here from this whole presentation because it came up as a question. You want to be in full. So if we go look at these models, right, and we go to speed settings, actual speeds. Well, actual speed's kind of messy. Let's go to regular speeds. You can see that it's all kind of basically solid. I got some under infill here, and we're going to go talk about speeds next. You want to be in full control as much as possible of all these speeds, and the reason for that is VFAs. You don't want the slicer to start changing speeds on you, and it does. And a lot of people don't realize this. So you'll get something here, and it'll look bad. And you're like, oh, I don't want to change the speed because I'm more focused on the higher speed value than the good print. So they come into the slicer, they go to filament, they go to cooling, and they start playing with dynamic fan speeds, cooling thresholds, which are like minimum speeds, like enable slowdown if layer print time is below. Turn all this crap off because all this stuff, messing with your fans while you're printing can leave artifacts. Yes, PLA prints at 100% anyway, so no big deal. On ABS, or the higher temperature ones, you'll start seeing artifacts caused by uneven cooling on the part because you are enabling different fan speeds to try and solve whatever print issue you have. It's better just to not deal with that. Leave the fan at some, even for ABS, leave the fan at some set point and develop the slicer around that, because it's harder to control the fans for this stuff. And so you just set the fan speed at 100%, and then you can develop your slicer. These guys here is probably one of the worst ones. To slow down if layer time print is below, right? So basically it's saying, let's just cut it here. It's right here. We have fan speed, 100%. If you cut this thing down with something prettier than that feature type, right? If this is doing a layer here, if this layer is too short, let's get a short layer. A short layer here. Okay, this is probably short enough. This little layer here, it's going to be less than, say, 10 seconds. I'm going to slow that down, right? But it's not just this layer. This layer is also less than 10 seconds. This layer is less than 10 seconds, right? And you go down and maybe you get to something like, come on, why won't my mouse work? Maybe, let's just say something like, this is not 10 seconds, right? So this was not going to slow down. But everything above this potentially could, right? So that's like half the model. You're going to start seeing VFAs in this side, in this model. Because what it's doing, it just gives you a minimum print speed. And if we go back, we'll go back to the presentation now, right? You may be setting a value at 125, but the minimum layer time says, oh, I can go all the way here. It's assuming this whole region is a good speed, but it's not. You have this bad speed, you have this bad speed, and there's another one over there. So it's going to slow you down, and it may end up right here. And you're all of a sudden you got VFAs. Why do I got VFAs? Well, it's because you printed at a bad speed. So we'll get to this slide. Where's it at? So before you do this, you want to be in control of the speeds that you're setting this thing at. That's the whole point of this. Turn this thing off. Just disable auto cooling. I know Prusa brought in uniform cooling, and they brought in consistent surface. Turn it off. Just turn it off. The Shaketune is good enough to tell us the speeds that we can print at, that we can set the slicer. We don't need any slicer tricks to do this. We need to be in charge of our speeds. So there's that side. So now that we've done that, we're going to be setting our velocity speeds. I'm going to use these interchangeably. They're effectively the same thing, and I've been saying them, kind of changing them already. This is VFA, right? This is a picture taken from Anna Rar on the Voron Discord. That's VFA all day long. That's your belts, right? We can try to minimize that. There's two kinds of VFAs, right? One caused by belts and one not caused by belts. The belts are going to be everything that's 2 millimeters, right? And that could be anything from belt tension too high, belt tension too loose, to you're pushing the speeds at the wrong speed zone. Right, so what's the solution to this? Is we start looking at belts, we start looking at tooth idlers, we start looking at bearings. Something is causing the pattern on the belts to make it to the tool head. So we can try to fix that. This is what we're going to try to get rid of by changing speeds. Okay, here's some more stuff that's related. I just brought these pictures just to show you. This right here, you see how it's kind of jaggedy over on the side? It's not smooth, it's kind of jaggedy, and you have this dip right here. Alright, dip right here along feature. This is actually a better one to show you. Okay, right here. That's all pressure advance. We don't have a very good pressure advance. You see this little dip right here? And sometimes you'll see it over here. That's not ghosting. That's pressure advance. And you see how it pops up again? So it goes light, dark, light. That's not ghosting at all. That's pressure advance. There's actually no ringing or ghosting on this model. That right there, that could be your retractions, potentially cooling. You can see cooling issues here, little cooling here. That's cooling issues. This might be ABS, I believe. If it's PLA, you're running way too fast. If it's ABS, you need to turn the fan up more. But that could be retractions. This is an extruder issue right here. Because this will print slower. It could also potentially be a bad speed, bad PA right there. So there's no VFAs on this. Sorry, let me rephrase. There's no resonance on this. This is all other printing things that we will talk about later. Okay, so this right here is speed. This is speed related. All this in here, speed with probably EM. If you notice, like you see this, right, see that right? Oh, can you guys see it? Let me see if I can make it bigger. You see this up here? These little vertical lines right here. Very tiny, they're right up here. That's all motor VFA right there. That's bad speed. They're not 2 millimeters. They're less than 2 millimeters. That's motors. And you'll see it on the Voron cube. You'll generally see it here on the bottom. And you'll see it up on top. Sometimes you'll have a band across the middle. You'll see it. This right here is potentially the bad motor speeds, which we already know we're printing at, and EM or extruder related. There's your PA over here. That's not ghosting. That's PA. There's actually no ghosting here. You'll get a little bit, almost like a chatter, right? Like if you're doing CNC work, you get like the little chattering. You'll get some of that on this, and that's you PA, EM, bad speed, right? PA and EM are underrated in what they do to your model and make it look like other things. So there's on this one at least, this blue model. Let's get out of here. Come on. These two, there's no resonance issues in that, or from acceleration. Now this might have some, because the VFAs are so bad, it would hide it, and you also don't have any feature sizes. So it could be from this corner over here. If it's printing this way, it could be. Some of this could be VFAs. Oh, I'm sorry, ghosting. Definitely has VFAs, could have ghosting, and one can hide the other. It depends on the feature that's here. So we'll just have a straight line here. They could be working together and making it look like this. That's why you need features like this or the tower test that I'll show you later. So what do we get? We get this setting velocity speed from Shaketune. Okay. We get. I'm going to go all the way back, guys. I apologize for doing this, but we're going all the way back to show you the test. This is a vibrations test. What are we going to use from this? We are going to use these two graphs: global speed energy profile and angular speed energy profile. We're not going to really talk about these right now because it's not going to help us set our graph. Well, it will, but it's not enough to go into right now. Two graphs. This one here does all of the angles. So from 0 to 360 degrees. It does all the angles of the motors. This one here gets you your X and Y and your 45 and 135 angles. Your motors, your A and B motors on a core XY are at 45 and 135. Those are the motors that are excited during the test. Then from that, it extrapolates the X and Y mode, the values. You'll use this one for purely structural. If you're printing boxes or mainly structurals with parts with hardly any angles or turns in them, right? So if you would use this speed here, these here, the angular speed energy profile. If you're printing organic shapes or even printer parts with wide sweeping turns, you're going to use the global speed energy profile. Okay, so in the global speed, organic structural, we're going to do everything based on this because it's easier. People, I think, see the green and like, oh, that's a good zone. I can use that. Okay. Just because it's green doesn't mean you can use it. So you have some very small green areas. If you have like just like a sliver of green, I would not use it. Okay, these are 3D printers. Yes, they are can be precise and accurate, but there's also the dynamic effects which aren't being taken care of. I would use this big green zone and try and find a good maybe right around here, maybe here, anywhere in this. If this is much smaller than say 10 millimeters per second, a green zone like this, don't use it. Don't use it because you're going to have to drop to the next level. This is about 10, and I'm going to use it. Also, you can go outside of these a little bit, right? These are just like calculus. A lot of this is best guesses, right? Based on some calculations. You can go a little bit out. If you're noticing that green zone is giving you a little bit bad, if you speed it up a little bit, does it solve it? Does it get rid of that issue? If so, go with it. So these, I would treat these all as very good suggestions, but not something to, use as your last stand. So if you're doing ABS and other high temps, go ahead and go 125 millimeters or higher. You can do it. ABS, even on a stealth burner, you could do it. If you're doing PLA and you're not doing any server fans and you're not doing any CPAP, you're going to be 125, 150 and below. You're not going to have enough cooling to deal with the higher speeds. So, and these are going to be your infills too, in PLA. So, perimeter is 125 below. Infill, yes, you can go 150 because it doesn't have to look pretty. But remember, we want at least the thread to go across or the string to go across on the infill and make full connection and not be broken. That's going to be your limiting factor on that. So as with accelerations, we are going to start with our internal external perimeter speeds. So there's a lot of text here. I'm just going to explain the graph. You guys read the graph text while I'm talking about the graph. The internal, no, I got these mixed up again. Let me see here. Externals will take time. So, okay. That should read external perimeter. Your pretty things are going to go slower. So you start with your internal, external the same. Okay, so we're going to start with internal, external, both at 125. You do a test print. Does your external look good? Right, from a cooling perspective, right, if we go back to here, can I actually cool the model off at 125 such that I don't get droopy Y's, droopy over here, and things like that? Yes, keep that speed. No, drop it down. Right? Because for us, we have two, for PLA, for most filaments, let's do most, two concerns on external perimeters. VFAs, which we're trying to accomplish with this graph, and cooling. If you can't cool the filament sufficiently for its needs, we're slowing down. ABS, you potentially could increase the fan. And remember, we're making a consistent fan. We're not doing no exterior perimeters, internal, we're just a consistent fan speed. So you might be able to say, if you were running ABS, say at 10%, and you're getting bad perimeters at speed you think you should be getting, just increase the fan and you'll probably solve your problems. The speeds are for VFAs, but for PLA, they're for PLA, the speeds are for VFAs and cooling, because we're already running at 100%. There's no 110% fans. We're not overdriving the fans. So that's why we're doing internals slower than externals, because there was no good speeds here in this range that would give me good feature sizes or features in an PLA print. So we drop to the next screen. Small perimeters. Okay. So BOSS, I'm using PrusaSlicer. This is the BOSS edition by Atomic Vector Plotter, AVP. Uh, he takes the best of Super Slicer. It's called BOSS because for his best of Super Slicer, he takes the best features that he likes that are most useful, and from Super Slicer, also takes features from Orca Slicer and puts it into the PrusaSlicer. It's a great. I like it. I understand Orca has a lot more features. I don't like the UI in Orca, and I've tried it. I've given the old college try. I don't like the UI, but I do like that they're doing new things. Atomic Vector Plotter AVP also likes the PrusaSlicer, and he wants more features. This is his pet project. Does have a GitHub, which I will post in the description. He's not going to just take a feature from, say, Orca Slicer and put it in. He wants to make this thing. He wants the features he wants that are helpful to us, but he wants the least amount of maintainability in it. So he's going to wait till it's out of beta, it's out of alpha, it's been fully flushed out, been proven to have a feature that actually is helpful, or gets incorporated into PrusaSlicer. So he will pull things out. Just as an FYI, if you guys want to start using it, he's not. If you start doing like pull requests for the latest and greatest thing, for example, bricklayers, right? That's doing the different shifting of the perimeters. He's not going to put that in this thing because that's maintain. He doesn't want to deal with the maintenance. Just to let you know. But I like using it. So what were we talking about? We're talking about small perimeters. It has something called the BOSS edition has something called small perimeter threshold. This is set. I've set it. It's not the default setting. That's the setting I set at 10 and 30 millimeters. That is set for the size of an M3, M5 screw hole. So what is a small perimeter? If we go back to here, it is a hole inside of the bigger thing. Right? So if this is my model, this could be considered my small perimeter threshold. And we can go here and we can say, does the speed change? Okay, so it's gonna, if this circumference, I should say, is within the range of 10 to 30 millimeters, it will use that speed. It will use the small perimeter speed. That's what it's doing. So you can set this on a per model basis. If you start seeing your holes in the model, M3, M5, or whatever kind of hole you have, start not printing as nice, you can adjust the threshold. You have to figure out what's the diameter or what's the circumference of that hole, and then you can start playing with the accelerations. I leave it at 10 and 30. It's working for me. It can be a per model adjustment here and a per model adjustment there. I leave it at 1030. Works for me. But that's going to go slower than your external perimeter because you want your hole to form. If you're doing a screw hole, you want your screw hole to form nicely so that you don't got a bunch of junk when you're trying to put a screw in, right? That's basically it. So that gets dropped slower. Infill speed. Sparse infill. You're going to want to go, once again, this is back to the previous discussion, push it to as fast as the combination of your speed and acceleration you determined from your speed test. If you notice broken stuff, slow it down. Right? That's it. It's just slow it down. You don't have to run everything at 11. So you can start with your internal perimeter and infill acceleration. Internal perimeter is fine. If you if you notice, if you start at these internal perimeters and infill acceleration, if you notice you can go a little faster, go a little faster. Choose the Excel first, then increase the velocity. Solid infill, just start with the internal perimeter speed. It will generally need to be slower than sparse infill. And top solid infill, you can start with your external perimeter speed, and it needs to look pretty. So basically what we have here is we have external perimeters and infill over here. I'm sorry, internal perimeters and infill over here. External perimeters down here, everything else down here. All slow speeds. If you have a problem, if your infill's up here, you can, who cares if it's in the green zone, right? So if you want to push it this way, because it's infill, you're never going to see it, push it here. Infill can go disregard this entire graph, really. You are going to be limited in your material and your cooling rate and you know, accelerations, just because it's going to have some point where it's just going to be broken, but you can really ignore, infill can ignore this graph. But I do it at I think I do it at 150. Let's see. Where's it at? Right here? Alright, so what am I running my infill at? 150. 150 at 30,000 Excel. It does fine. I don't have a problem with broken infill. And I don't want to start messing with it because infill does crazy things. It's not always nicey-picey. And crazy things, what I mean is, if my thing didn't crash, crazy shapes, right? Depending on your infill. Well, it's got to reslice it. So let's see here. All right, so you can see the infill. It's not all perfect boxes like it was with the Voron test cube. It does these little things here and here, and it comes here. Feature type. Let's go lower. Right? It's not all nicey-picey, so you're not going to have always perfect grid layouts of your infill. So you don't want to go crazy with it. You can, and as long as you get good results, you're fine, but be reasonable based upon what you print, what you expect to happen, right? Because this infill is going boom this way, then it's not coming back straight and going straight down. It's following this little curve here, right? So yeah, just don't go crazy. So as you can see, I get started here, did some test prints, ended up here. I was able to push external perimeters better, had a little VFA on that, push it up a bit, done. Dynamic overhang speed. These are your overhangs. At 75%, what it means is your model underneath it has like 75% coverage. Excuse me. We'll show it here. These guys have overhangs. We'll go to the speed. We could use actual speed, right? So that's the actual speed, but you can see it's constantly changing. It's not constant. The speed here, it's more of a gradient. It's just easier to see. You can see this gradient right there. That gradient is our dynamic overhang speeds. So we'll leave that. Let's do this. Let's do this. Let's do the is that good? Yes, colors. Okay, so we'll go back to here. This blue is about 15 to 28. 15 to 25. So that's blue is somewhere between 0 and 25%. I'm going to guess it's 25% overlap. Then we go drop down to 50. So this light green is 50. And then speed for 75 overlap is 65. It's going to be a lighter green. It's a lighter, so it's a blues are about the same color, lighter green. So here you can see we go from like 0 or 25% overlap to 75% overlap to greater than that, right? That's going to be all this yellow stuff. What it means is, let's see if we can, it's probably better to go for the bottom up. Okay. How are we going to do this? Let's get rid of its head. That's probably good view. How much is this exterior perimeter resting on the perimeter below it? What's the percentage? And as we go up, you can see that you see it getting. Let's see if I can go in bigger here for you. You see this getting kind of looks like it's starting to get bigger. It's getting darker. Pull it here. See the width here, and the width versus something like over here. And right there, you see that? That's almost the entire perimeter hanging out. Versus how much here. This is your dynamic overhang speeds that we're going to be setting. If you go too fast, you say, screw it, I'm turning this, where's that setting? I'm going to turn this setting off. You're going to go way too fast, and these things are going to fail. You're going to start getting that droopy stuff and whatever. You need a gradient of speeds for this, because we're not using cooling, we're not using layer times, right? We are in charge of our own speeds, and this is how we're going to take care of this. So that's what it's doing. How do we set those? Is the question. All right, it's going to be testing, so we're going to need a model with an overhang. I choose all my toys have some sort of overhang. 75% external perimeter speed. 50%. We're going to start at the external perimeter speed or the next lowest down. So this is going to be our 75. We're going to start it at 75%. Will be here, the same as our external. Remember that's wrong. External perimeter speeds. 50%, we're just going to drop it down to the next green zone. So we're going to go skip down here. 25%, we're going to start at the 50% or make it half of 50 so long as it's still in the green zone. And 0, just leave it at default. Just go, you're going to go slow. Let it go slow because it's hardly any of the model. It's hardly any of the model. Whatever model you're doing. Where's that at? Alright, so that's where we get this. And I ended up with 65, 50, 25, 15. 65. So I started here, ended up down here. And that's quality. Right? I needed to go that slow to get the quality. And that's what we talked about. Alright. This is your rest of your speed settings. A lot of this is going to be actually going through and testing it. These are just defaults, as I said. If you start seeing a feature that's not printing right, you will slow it down. Or speed it up if it's if you're in a bad zone. The gap fill. Gap fill is... Do I have any gap fill? Oops. I'm going to go all the way up. We want to go to feature type. Gap fill is white. Always. So that's actually seams, I believe, too. Let's turn the seams off. Where are the seams? Alright. Gap fill. Right there. Right there. So it has a little bit of a hole there that the infill couldn't reach. It's going to come back in and do a dollop of daisy right there. Gap fill. You don't want to go super fast with this stuff because you're putting just that little dollop of filament there to cover that hole. And if you go too fast, you're going to get things are going to happen and you're going to get a bad model at the end. You'll be like, why is it bad? You're going to chase your tail. Just let it go slow. It's hardly, it's what is it? It's 11 minutes of gap fill in this whole model. You can do other things like changing your perimeter width or your line width to try and reduce that. I mean, if you want to speed it up, speed it up. I do gap fill at 20. I probably could go faster. It's probably too slow. It's working. It's 11 minutes out of a 9.5 hour print, and that ain't ever going to go to 0. So what am I going to save? 5 minutes? So it'll be 9 hours and 25 minutes for a print. You could say, well, all these little savings will add up. It's not going to add up. The biggest savings I got was going to all-wheel drive and increasing accelerations. You're much better focusing down here on your accelerations than trying to get rid of features or speed things up in velocity. If you have to pick accelerations, not velocity. So that's what I did. And that's where I got that. Ironing, I don't know. I have no idea. I don't use it. I tried, gave it the old try. Yeah, and it's not worth my time to figure out, really. So if somebody else is probably going to be an expert on how do you actually set an ironing speed, it's not going to be me. So that's those. Travel speeds. Highest you can go without skipping a step. First layer, you can go slow. So what are my first layers at? Let's see here. First layer speed, 50 millimeters a second at 5,000. You want to stay in the green zone just to kind of give you a base part. You don't have to, though. A lot of stuff is you don't have to. Got 50s right here. It's fast enough. I don't really care about VFAs. I just care about making a first grid layer. So a lot of the tests and I'm going to back up here. A lot of the tests we run are single models. Okay. Our VFA our tests on perimeter speeds and excels our test cube, right? It's a single model. Our first layer is a single model. That's good to get going. A lot of problems happen when you do multiple models. You'll start seeing new issues. You're like, well, why am I seeing this? I wasn't seeing it with this. Because you start moving around, and you're going to start seeing the resonance, potentially the motor vibrations happening at different places. So a good way to do this would be to create a speed, create a profile, and we'll go through what the calibrations look like after. And then print one actual model that you want. If it's only one, don't worry about it. If you're doing production like I am, start with one, see if that one comes out. So what I would do is I would print one capybara. Then I'll take a model, I'll build my plate up, and I'll put it where I want it. I'll print that capybara, see what it looks like. If it looks good, I go continue. If it doesn't, I go back and fix stuff. Then I will print a model diagonal to it, like these two. And the reason I do that is because I now have travel between the two. It's going to be doing Z-hops. It's going to be moving. I may pick up something that was borderline on a single model. But because now I'm jumping between them, it's no longer borderline. I need to fix the speeds and accels, potentially, between the two models. So once I get the two models done, I'll then go 4 models. And this is all part of my verification process. Once I got the 4 models, I'll send it. I'll just fill the plate up and send it, or fill up the plate to the time period I want and let it go. That's how I print to make sure that I'm printing thousands of these things. Right? I'll print 300 capybaras at a time, just one right after another, 300 to 400. So that's how I do it. I don't mind spending the initial time to do what I'm doing, because at the end result, I just keep hitting restart, and they all come out. So where are we at? So first layer speeds, we're at first layer speeds. Go slow enough to get a good layer, or go slow enough to get a good layer, fast enough that you can, continue on. I like the higher end of the bottom green zone, which was 50. Right, this is fine by me. It doesn't take a lot of time really, and it makes sure you have it will tell you if you need to clean your bed plate without wasting a lot of filament, and you can go outside or do something else, come back. You're still first layer still finishing up, and you're like, okay, I need to clean the bed plate. You can stop the print and go and do that. All right. So what about ABS? you're going to do a couple things. You're going to run, it's going to effectively be the same procedure above, but you're going to run this motor vibrations to either 400 or 600. You always start at 0. You always start at 0. PLA you can run on my machines. I just need this range here. ABS you can go from 0 to 400 or 0 to 600. This one looks really nice. Other machines you're going to get some junk here. Right around here. So depending upon it's a motor, driver, motor current, run current, and PWM, and it's also going to be your microsteps is going to really affect what these graph looks like. All motors, all systems will have this dead zone in here, right here. They will all have it on the lower ends, which makes PLA troublesome because you want to print in this area because it's good speeds, but they're not good speeds. So ABS, you can start doing your external perimeters here, right, and then build it up the same way. You can see I use this one because this one over here is a little bit better for it on this machine because they're flatter. You can see where they're at. But you will get junk here too, and you'll be doing the exact same procedure that I gave above. All right. Once you have now all this testing we've done, we actually have them printed, right? We've just created the slicer settings to get us started for our machine. Then you're going to do, after this, we've run Shaketune, we've done the slicer. Now we're going to do PA and EM. After we do PA and EM, we're then going to actually do our test print. So the order of calibration is E steps, belt shaper, input shaper, back and forth on those till we get good graphs and we have good speeds, or get good graphs, and we know that at least our tension system's there. So here we've sorted out mechanical issues with our build. Then we run vibrations profile using the values we got from input shaper. Now we're set. Then we set up the slicer as we've done it. Then we're going to do our first layer cals. Right, so we're going to make sure that we can print a good first layer because now it's our printing testing. There's some discussion about which one of these goes first. Does EM go first or does pressure advance goes first? Ellis print guide says PA goes first. I talked with Frigg at Portland Vice. He recommends, and he's a PIF provider, and he's got his little farm. He's from France. Nice guy, really great guy. He says do your EM first because you want your EM to look good when you test your PAs. Right? You don't want that to be a factor in your PA. I don't know. I'm probably gonna start doing what he said, the order he said, because I mean, his prints look even nicer than mine. So I'm assuming he knows he's done it before. So the orders, this is the order I currently do it in. I might start trying it out in this order. And for EM, what do you print? Calibration cubes. This I'll put the link to this too in the description. These are basically different PA values on the bottom. So if can we get to it? Let's see. Boop, right there. So once you print it, you already know what they are. And there's a whole range of them. In BOSS, you can right-click a thing. You add a setting. Let's see if I can figure out advanced extrusion multiplier. So you can set the extrusion multiplier for all these objects, and you can print it, and then you'll see on the top surface what does the top look like. I print it using my regular settings, kind of like what PrusaSlicer does. A very similar test. This is a very similar test to what PrusaSlicer does. And any changes I make, put in here, and I can see the effect on the extrusion multiplier. For PA, pressure advance. What is it? This is your pressure advance. Figure that this is your extruder velocity, and you're moving around. You're going from you're taking off from a corner, and you're going forward. Right? You made a turn. You've adjusted your you're slowed down, you have to adjust your pressure advance, now you're taking off again. This is the acceleration giving on that tool head. Your pressure advance is going to be the orange. This is what it's like to compensate for this. This is how much extra filament we're going to put out. You can think of it that way. So that's your PA. That's what it's going to do. Your smooth time is going to come in here and smooth it out. Right? So you don't end up with like this little blob. You want a little smoother. When you adjust your smooth time, you adjust this. You see how it kind of hit the right in the middle there? You're going to adjust this out. Tighter, narrower, whatever. Something I learned, I never really adjusted smooth time. I kind of just let it go to like either 0.03 or 0.04. Something I learned was that Frigg stated that smooth time should be half a PA. I don't know. I haven't tested it. I will be testing it because it's very interesting. How would you actually set smooth time? That's how he does it. I think it's worth trying out. But generally, I set my smooth time to 0.03. It's once again, it's this how long it takes to do this here. My pressure advance is usually around 0.036 to 0.038. The faster you go, though, right? The faster your square corner velocity is, the more you're going to need to adjust the pressure advance. What's a good test for pressure advance? Right, you have the Ellis print guides, the chevrons, the other stuff. Print a box, right? So what is this? This is a 40 by 40 by 20 millimeter box. Use your own settings that you have. You want 0 tops. You can do 3 perimeters, bottoms, whatever. Leave it at 4 or whatever. It doesn't matter. 3, and then set infill to 0. Let it slice. Where'd it go? Did it walk away? Oh, sliced the wrong plate. There we go. Okay, so you start off with pressure advance equal to 0.04, the standard one, right? It's going to be in your printer.config. I believe so in the Voron config. You set it there. Then what you do is you use this command, set pressure advance. We'll get rid of smooth time. We'll just like block that off right now. Set pressure advance. Advance is equal to 0.0. It'll be 4. This is the command you're going to put in the console to change it. So as it's printing, that's the command we'll use. As it's printing, we're going to look in the sides and the corners. If you have gaps in the corners, drop down your pressure advance. If you have gaps on the sides, increase your pressure advance. If you have gaps on both, try lowering smooth time. But it may be the extruder that's going wrong. So generally what will happen if you set it at 0.04, for most tool heads that a Voron uses, you'll get a gap. Just keep lowering. You lower it just a little bit, so you'll go from like 0.04. Is it 0.04? Yep. 0.04, then like 0.039. Try that. If it closes, you want to let it go at least another layer, a layer or 2, right? Because you really want to make sure that that command got put into the motion queue for Voron, for the clipper, and then it's being actually used. Because it's not instantaneous utilization, right? You do a command in clipper, it's not instantaneous. It has to go through the motion queue to get set, or this queue, or command queue to get set. So give it a couple layers, and then take a look at it again. And if it needs more adjustment, make that adjustment. And then, so that's pressure, extrusion multiplier. Oh yeah, there's the cubes. There's the cubes right there. You're gonna have to initially, the first time around, you're gonna have to set each cube's pressure extrusion multiplier, and you'll print those out, and you will use what Ellis says about what's supposed to look good. And then that's it. That would be that. Now, what test prints can we use to verify all this junk? Well, we have the standard Voron cube that you've seen. You have, we've gone through a couple ones, but this one for input shaper to verify it, we're going to use the model, but we're not going to use the commands because we just want to verify it. So grab this model. Let's see where I have it. Right here. You don't need to print the whole thing, right? So what we're going to do is we're going to do a negative volume. We're going to do a slab. A slab or box will work, right? We're going to go like this. We're going to bring it up, and who cares because we're not doing exact. We're going to stretch it out. And we're going to come down here. Oop. 1, 2. That's probably good enough. 2.5. 2.5 of these little things. Send it. Hit slice. This is a model. Now we do lose the X and Y on the side, but who cares? Because we're just verifying it. And then this can be a verification of your. It's going to be your external perimeters on the outside all around. You can also use this as a VFA test to test your speeds. All right, because if you start seeing little fine lines, you know it's a VFAs, which is back to your speeds. If you see ghosting, it's going to be your accelerations. So you can use this test. And we don't need to do the whole clipper. We're not using this to test input shaper. We're using to verify. The other motor vibrations print. So let's say you want to do this, but you don't want to have Shaketune or can't install it or just don't want to. You can use Mahahi Designs. That's the link. You can run this test. And you can run this as a verification too to vibrations profile, and you can see he's got. This is his. Let's see here. Boop. VFAs. That's not ghosting. That's VFAs, and you can see how they kind of fade out, and then boom, some more very fine ones here. And they're kind of like from 0 on his printer, whatever this was printed on. There's no real good slow prints. There's no good slow prints, and even here, it looks good there. It's right there. You don't start getting good prints till about 150 on this one. Right around here, 150, 160, 170. You start getting very fine VFAs. These are mainly your belts down here, and then you get good again. Like you see, this is that kind of that chattering I'm talking about. I was talking about earlier, where it's kind of like. Is it something? Is it not something? It is something. It's just kind of a pseudo good zone, if you will, like that stuff right there. And if this wasn't above it and this wasn't below it, you wouldn't be too concerned about this. You're only really noticing this now because of what's above and below it. Same with kind of like this layer here. I'm only seeing this because I know the pattern goes through. If I didn't know the pattern was going through, I wouldn't be concerned. But this is also VFA. This is more motor. This is more belts, our motion system in general, and this is more motor right about here. So how long does it take to do this? Because you don't want to sit here. It's about a week for me. I do this in about a week. Why? I get so pissed off doing this. Let me tell you, this is going to be an exercise in frustration. Right, but once you get it done, you can basically do this for all your models. So you can use the same profile, and it's small tweaks after that. But I'm not gonna lie to you guys. It's a very frustrating, it's time-consuming, it's tedious. You're gonna waste a roll of filament, so just be prepared for that eventually for this thing. But at the end, you will have a solid profile for your printer. That's customized to your printer that will get the most out performance-wise of your printer. Is this for everyone? What I've done this whole thing? No, it's not for everyone. And it's some people just want to hit print and send. Some people want to tweak. If you just want to tweak and you don't want to do the full thing, at least now hopefully you understand where everything's coming from and how it all relates. And you can go ahead and tweak a standard profile without going through all of it or without doing some of these test prints. But at the end of the day, this is all for good prints, good quality looking prints. Not the 100% like PIF quality. I don't know if you guys know what PIF is, but their stuff is like immaculate. It's about 90% of the way towards their stuff. Just what I do, I don't get 100% of the way. I get 90% by doing these steps and verifications. Uh, I'm also, as you know, also the chief elf of 3D printing elves. We're having a raffle to raise money. We print toys for kids of the Central Valley of California. We do it not just at Christmas, we do it all year round. Last year we donated 5,000. This year we've donated up to this point, October, what is it, 11th, 13th, October 13th. We've donated 12,100 toys, and we're going to keep printing. So that's why the quality of toys matters, because these are going to uh, very low socioeconomic students, our kids. We donate mainly to schools. We've also donated to places like CASA for um, foster youth, UCP. We do go, well, at the end of the year, around November, we'll kind of stop the toys going out other places. We'll take all the toys we have and give a percentage of that to Toys for Tots. But we found that it's better to give all year round instead of Christmas. And the feedback from who we've given to, especially teachers or educators, is that they use the toys throughout the year, as in treasure boxes or for special needs kids, as fidget toys for them, or as rewards. Say your kids in speech and they had a really good day in speech, to keep them motivated, keep them excited. The teacher will give them a toy, and we're very proud that we're able to help the kids of our community. However, we need support, and one of the things we're doing to raise money is a raffle. We have a lot of great support. A lot of great people in the 3D printing community have helped us, are helping us out with this. LDO, West 3D, KB3D, Fabrico, Dr. Mercy, Cartographer, Additive Attic, Happy Manufacturing, Killer Prints, fantastic, Armor 3D, Lemery 3D. A lot of the community is helping us to prevent the prizes that you guys can win. It is a raffle. The tickets are $10 for one ticket, $50 for six. As you can see, we are giving away 5 different printers. Some of them are kits. Some of them have built on stream. Killer Prints printed or built the Prusa wire and the V0 printer. So please, if you can support us, it is only open to the lower 48 United States, and it's shipping costs. I mean, we are a small nonprofit, and the shipping costs to international or even Hawaii or Alaska would kill us. So if you can't afford a raffle, you can't do the raffle because you're not in the lower 48, but you still want to support us. We do accept donations from the raffle site. There's the site. It will be November 9th will be the drawing, which is a Sunday, and it'll be on Killer Print stream. So thank you for those who have supported us and helping us fulfill our mission. This was the question and answer time at Reno Vice. A lot of the questions I have incorporated already, but if you do have questions, go ahead and leave a comment, and I will try to answer it to the best of my ability. If you need help, I'm always on the VOR on Discord in the Basic Resonance channel. Go ahead and open a thread. Please open your own thread. That way we can keep everyone's issues separate and I don't get confused. Yeah, hopefully this helped you guys. If there's anything else you need from me, if something wasn't clear, please let me know. Leave a comment. Thank you, and I appreciate your time. Have a good night.